Hi, everyone. I'm sad to not be there in person. I'm dialing in from London, working over here, working on a problem I'm absolutely fascinated about learning a globally scalable driving intelligence. So I'm really glad to tell you a little bit more about this today. There are a few members of our team in the audience and around CVPR this year, so please do say hi and catch them if you do want to talk more about this. But this is, I think, this is the third time I've spoken at this workshop, and it just gets better each year. So I'm really excited to continue the conversation and share an update on what we've been working on at Wayve. So to begin with, here's a few videos of some of the experiences that we've seen driving autonomously on the road in London. And I wanted to share them to motivate the problem, because you can see some really weird and wonderful behaviors on the road. This is, I think this is truly a grand challenge for artificial intelligence. It's the next frontier of AI to bring representations and the things that we can learn into the physical world, because the diversity and requirements are absolutely enormous. If you look at this video in the bottom left, for example, we recorded it the other day, and you can see we're driving along and this double-decker bus is on the wrong side of the road coming straight at us. Or many other examples I can share that the level of reasoning you need is really extraordinary. Now, the question that we're posing is, are the current approaches that are being pursued by many people in the field about coding, hand-coded design following set routes that are mapped in each new area they go to, is this what's going to give us trustworthy autonomy at scale? Is this going to give us the intelligence to really drive and interact across all of these weird and wonderful scenarios? Now, 5 years ago, we set out and actually thought that maybe that's not the right way to do it. Maybe there's a better approach, leveraging a lot of the advances in machine learning that some of us have been fortunate enough to work on. And while that was incredibly contrarian 5 years ago, over the last 5 years, what we've been able to show, I think, is really starting to prove out this thesis. And it's not just in autonomous driving. If you think about image recognition, connecting natural language and vision, game playing, biochemistry, there's so many examples where deep learning is pushing the boundaries and even surprising me at some of the results. If you think about some of the work this year, such as DALI 2 or Imagen, for me, this has shown the ability for neural networks to bring together really disconnected concepts and bring them together in a way that can generate images that exist on the manifold of natural images. And you can point to some really extreme examples of I think I saw one image of a dog in a house made of sushi. And this is a natural image that is bringing together really disparate concepts into something that looks realistic. And well, maybe it's not realistic. Maybe the dog should have eaten the sushi. But what this shows to me is we can bring together data of a car driving through a roundabout in the rain and going through another experience of a car going through roadworks in the sun. And can we bring together these different concepts to be able to drive through roadworks in the rain? It really speaks to this generalization that means that we can deal with the cascading complexity of autonomy. Or even if you think about game playing agents, in my opinion, driving is probably a harder state space, but a much easier action space compared to things like Go or StarCraft. Driving, start, stop, turn left, turn right. Those are the basic motion primitives. Whereas in the game of Go has extraordinary complexity in its action space. So, so I think we can draw a lot of inspiration from these problems. And would you tackle these problems with a hand-coded approach? I think not. You'd be laughed at. And so I think the same is going to be true in autonomous driving. Now, the basic premise of what we've set up at Wayve and how we're tackling the problem is in a learning paradigm. How do we take our 10 to the power of 8 dimensional input of 6, couple of megapixel cameras and some other sensors, and compress it into a 10 to the power of 1 motion plan as an output? That's the fundamental problem. How can we construct this in a way where we have the right data and learning signals, as self-supervised as possible, to be able to learn to drive? Now, of course, we don't want to bottleneck the representation, but we can decode intermediate representations into human interpretable outputs that give us some level of interpretability. And I'm going to talk a bit more about that today. One of the first things we tried is building a model-free on-policy reinforcement learning system that could learn to drive and demonstrate that it's possible to bring some of these machine learning ideas onto a physical robot. And I was actually the safety driver in this video, and this was us in 2018 learning to drive down a quiet country road. Now, if we play this video forward, you can see after about 10 pieces of feedback where I grab the steering wheel and correct the car, it goes from knowing nothing about the world and being completely randomly initialized to, you can see after a couple of exploration episodes, it then learns a policy that can slightly correct, but it's still unstable, and ultimately it'll run off the road. To then later on, you can see it's able to drive and do so robustly and go up and down this road as many times as you like. So I think that was the first example of taking reinforcement learning out of simulation and putting it on a real life mobile robot. And we started to scale up. This was some of the work in subsequent years, bringing it to unprotected turns, to traffic lights, and ultimately where we are today, which is driving throughout London, doing all of the complex behaviors that you need. And this is with a single end-to-end neural network going from sensory input to motion planning output. And you can see the complexity of these environments, whether it's the very complex multi-agent behavior, the unstructured world that we're driving through. This is stuff that we test through every day. And if anything, London motivates this method going far beyond the structured environments that you see with other autonomous driving systems testing in desert cities or in highways. This is the ultimate test of autonomy, coexisting in society, interacting with people around it. I think this is, this is the real challenge. So that's where we are today, driving across London. And so what I wanted to spend time talking about in my keynote today was about some of the grand challenges ahead. What is it going to take to bring us from where we are today, a end-to-end neural network that can drive across all of the scenarios that you need for an urban driver, to something that really has the robustness for us to launch at scale and for us to more generally build embodied intelligence that we can trust. So I'm going to talk through a few items: adaptability, off-policy learning, uncertainty, interpretability, world modeling, and benchmarks and simulation. We actually talk a bit more about them in this archive paper that I've linked at the bottom if you want to read more. But I want to talk about the summary because these are, I think, some of the most highest reward items for us right now. So let me talk through them. Adaptability. This is, if you think about you're never going to see the same thing twice on roads. And so it's incredibly important to build a system that's capable of generalization, of adapting to new environments. And what we're able to show last year is we actually trained our system in London on tens of thousands of hours of driving data and took it to other big UK cities like Manchester, Liverpool, Leeds, and drove in these cities in a zero-shot test, having never been in them before. And I think this was quite an exciting demonstration. It shows that you don't need a high-definition map to drive. You can build concepts that can generalize to new behaviors. If you think about the roundabout we've learned to go through in London here, or demonstrating the same thing in Coventry, or driving in traffic, demonstrating that in Leeds. These are behaviors that we've been able to adapt to a new environment that does have a different distribution of scenarios. Now, what we've done this year is go beyond geographic adaptation to now showing multi-vehicle adaptation. This is really exciting because a different vehicle has different dynamics, different sensor poses, different sensor types, but we've been able to build a system that can map that to a unified representation and ultimately learn to drive with a single neural network, not only across different cities, but across different vehicles. So imagine the consequences of this. We have a single neural network, a platform model that exists across, we want to see it deployed across a number of fleets in a number of cities, and mutually learning from all of the experience that we have. This platform model is how we think we're going to see autonomy scale. Because ultimately, the way that we move and drive these vehicles is similar across all of these kind of platforms. So we want to build the best dynamics aware, scalable and generalizable neural network. And that's what we've now shown across different cities and now different vehicles. So this plot on the left shows a model that's trained, say, only on our Jaguar I-Pace vehicles in the top right. And you can see it achieves fairly good performance on the vehicle, but very poor performance driving on the van in a zero-shot setting. When we then train a similar model on the van, but with less data, you can see it is okay on the van and very poor on the car. But when you bring these data sets together and do multitask learning on both corpuses together, not only do you see performance on the van that mimics what happens when you train on a large data setting on the car, but you even improve the performance on the car itself. And so we get this, this great transfer learning effect. This is really exciting for me. Next point, off-policy learning. Now, of course, getting on-policy data is very costly, and what we're excited to now be doing is partnering with world-leading fleets and deploying data collection devices on their human-driven vehicles to be able to collect data at scale. And this is off-policy data. And so what we're very interested in is how can we effectively leverage this to improve our on-policy, our closed-loop driving performance. So let me talk through a case study, which was a really interesting one for us. The photo on the right, you might recognize it from the Beatles album of the Abbey Road pedestrian crossing. It's actually not too far from our office and something we drive through fairly regularly. But I'm going to show you a couple of results here. So first of all, we found that if you train on a naive uniform distribution of driving data, let's say you get a number of people to go out and collect some driving data, you train on it. Stopping for pedestrian crossings is going to be a very rare example, not something you naturally learn with a naive learning approach. So we thought, okay, if we can provide a feedback loop that mines this kind of data, maybe we can improve our performance on pedestrian crossings. So how do we do this in a self-supervised way? Well, we can detect pedestrian crossings with computer vision models and some semantics. We can look at the uncertainty of our neural networks and actually pick up where our system is ill-performing. Or we can use other, leverage other databases like some of the OpenStreetMaps or other low-dimensional mapping data to isolate some specific examples from our GPS sensor. All of that lets us evolve this curriculum. And the great thing is what we find is when we improve and adjust our sampling with some of these techniques, we go from a system that doesn't perform, and as in the top video you can see requires an intervention, driving up to a pedestrian crossing, to at the bottom, quite a robust result that can go through a number of pedestrian crossings accurately, stopping for pedestrians, predicting when they're going to step onto the crossing, and ultimately yielding and pulling away when it's safe and legal to do so. And so that's through off-policy learning. We didn't do any on-policy exploration. It's simply through adapting and adjusting the data distribution from our large-scale collected corpus of data. Next, uncertainty. Well, this is a topic I spent quite a bit of time working on in my PhD. And here I'm showing you some results that have allowed us to use Monte Carlo dropout sampling to form Bayesian neural networks that can estimate various forms of uncertainty, in this case, the semantic segmentation model. Now, this is great because we know how to understand differences in uncertainty, where aleatoric uncertainty exists, perhaps due to the sensors that we're using, or epistemic uncertainty that is resolvable by improving the model with more training data. So there's various forms of uncertainty, but the neat thing is not only does this apply to perception, which is what I've personally worked on in the past, but also to control. And here you can see an example of us on the left driving, doing an unprotected right turn. We actually do it successfully, but you can see here the motion planning output and the various uncertainties around it. Now on the right is when we aggregate this uncertainty metric about our motion planning output across all of the interventions that we see over a period of time. And you can see there's a fairly consistent spike in uncertainty in a couple of seconds leading up to that intervention. Now, this is interesting because it provides a platform for us to really build safety criticality into our system. How do we know where our system is uncertain or isn't able to go through a certain scenario? How do we know when to pass back to fallback strategies or remote assistance? Well, now we're seeing that neural networks are not as much black boxes as they were in the past, but now we can actually interrogate them and understand what they know and what they don't know to be able to drive data curriculum and improvement, as I showed in the previous example with off-policy learning, and also improve safety and trustworthiness of our system. Interpretability. So I think this is a really important point, maybe not so much to expose to consumers of autonomous driving, but it's very important from a engineering design and trust and regulation point of view. How do we understand the causal factors and decisions? I want to show you one interesting result that our team got recently, which is when applying a visual transformer to learn to drive. You can see that with a transformer, we can look at the attention mask and actually actually see what the neural network is paying attention to in order to make that driving decision. Now, this is interesting because you can see that when we pull up to these traffic lights, you can see that it's very attentive on the red traffic light. Now, when it goes green, you can see it switches its attention to the road and actually looks to understand, is it safe to pull ahead now that it is clear to do so? This is interesting to me because it allows us to start to reason about why, maybe not a causal reason, but at least the correlation for what part of the input signal is affecting the output decision. And this is really useful for checking that we are making the right causal decision and we're not causally confused. For example, some of our earlier models, when you're parked at a traffic light, often we might be parked there because other cars have stopped. I actually was in the car once where a car, with one of our earlier models, where a car was beside us parked at a red traffic light, and that car pulled ahead and went to go through the red traffic light. Now, our model actually tried to do the same thing because it had paid attention more to the car than it did to the traffic light. And in fact, a more prevailing pattern in the data was that cars stopped at, your car should travel a similar speed to other cars around you was more prevailing than you should follow the signal of the traffic light. That's an example of the wrong causal effect. But when you introduce things like this and some of our more advanced models are actually able to pay attention to the right factor, which in this case is making sure you yield to the traffic signal. World modeling. The worlds we drive in are really dynamic, and if we're going to see benefit from autonomy at scale, we've got to be able to operate in incredibly complex and dynamic worlds. In our case, in busy urban cities. Here's a good example of why we need to be able to reason about temporal context and predict dynamics. If I gave you this image, could you tell if we should yield or how we should behave around this car, this white vehicle on our left? Actually, it's not until I give you the video you can tell that although it's pulled out of it, it's actually stationary and it's safe to drive around it. So this illustrates the importance of temporal reasoning. Now, at last year's CVPR talk, we introduced a model called Fiery, which was able to do multimodal, diverse, and plausible future prediction. This is really exciting because we could model a future distribution with privileged data at training time and align this with a divergence loss to our present distribution so that we could sample from it at inference time and actually understand probabilistic and multimodal futures by jointly modeling the world around us and our own motion. Now, if you want to read more about this, this was in a paper presented at CVPR last year. This year, we've extended this not just to future prediction of the world state, but actually also drive the model. So this is model-based imitation learning. And we're really excited about this work because it's able we're able to now extend it to really long time horizon, stable dreaming, stable imagination. You can see the video in the bottom right that's doing over 60 seconds of imagination. What it's doing is it's leveraging 3D geometry, it's decoding into this bird's eye view and predicting forward on a really long time horizon. You can sample different modes and see the different things that might occur in the future. But ultimately, it lets you robustly understand things at a really large scale. And we're excited to see it reach state-of-the-art performance in the Kala simulator, or at least a few weeks ago, it showed 35% improvement over previous state-of-the-art, which I think was the fantastic work by Chen and Cronenbol. But it avoids things like the worlds on rails assumption that came from some prior work and is able to use these rollouts to really inform and improve the control policy itself. Here you can see some of the multimodality. So this is a stopping at a traffic light intersection. Well, at least one of the imagined futures, the imagined futures you can see on the far right, imagines that the light stays red. The other one imagines that it goes green and we pull away. And you can now see how there's some quite distinct modes that it's able to learn that are quite different. And when you bring it together to do control, you can see this is some of the driving performance we see. And so just some examples. And this is all with just camera input. So no, and route map. So no LiDAR, no radar, no additional sensing modalities, just vision and just monocular vision at that. So we're really excited to see this brought into control. Finally, let me talk about benchmarks and simulation. I think this is emerging as a really important point to see innovation on to drive forward progress faster than we can iterate on the real roads alone. So on the right, you can see a rendering of our simulator, and simulation is really interesting when you're looking at an end-to-end learning approach to driving. You need a completely different approach from other simulators you've seen that model, I guess, top-down object representations only. You need to be able to model end-to-end, including perception and vision. Now, the other difference in autonomous driving compared to what we might be used to in computer vision with benchmarks, if you think about some of the benchmark data sets that have really pushed forward state of the art. In my PhD, I worked a lot on the cityscapes, the Kitty data sets, but a lot of these data sets for perception tasks are static, train and test. But in robotics, we need to be able to test in closed loop. We need to be able to look at interaction with the environment. And that's why simulators like some of the ones I've listed here, Majoku, Kala, Go, have been really important to drive forward development. But and why they're so important, it's interesting when you look at a number of breakthroughs, whether it's some of the breakthroughs of seeing AI systems first learn to play chess or solve ImageNet. A lot of these ones weren't actually catalyzed by the algorithms themselves. Like if you look at ImageNet, convolutional neural networks came from the 90s, but it was the data that really made, I'd argue that really made breakthroughs like AlexNet in 2012 possible. And that data only came about in the late 2000s. So data sets and benchmarks are really important to catalyze progress. And we see closed loop benchmarks as being an important one for embodied intelligence. So what we've built is an end-to-end simulator that can procedurally generate diverse worlds. So they're all randomly generated, including the geometry, the visual, the appearance, the behaviors of the agents. We use both scripted and emergent behavior that comes from training reinforcement learning agents in here. And each time you have a different random seed, you generate a completely different world. This is really powerful for us to test at an enormous scale that hasn't been seen before in the industry. It's possible for us to really understand and not only look at a large variety of different scenarios and behaviors, but also to see emergent behaviors emerge that we might not have seen in the real world before. This kind of simulator lets us get results at a speed that is orders of magnitude faster than the real world, and is becoming our primary tool for development. We're really excited about it, seeing it accelerate what we can do on the real road. So I hope a bunch of these grand challenges are really interesting to all of you. We certainly find them fascinating to work on at Wayve. And for me, I think the conclusion that I take away here is that embodied autonomy is the next major frontier. It's often been said that you can't build artificial intelligence without interacting with the world. In fact, neuroscientists believe that the whole purpose of intelligence is to produce adaptable and complex movements. And so I think we've got to, as a community, bring AI out of data sets and simulation and software and actually bring it into the physical world. Autonomous driving is going to be the first large-scale example of that. We believe at Wayve that a learning approach is the way to scale this, and for many years we have been on the forefront of pioneering and deploying on physical robots and fleets with end-to-end embodied intelligence. And we believe that using scalable and low-cost sensors and really leveraging data at scale is the way to achieve this. And hopefully some of the ideas I presented today show you some of the advances we've had towards solving the grand challenges of autonomy. It's a great problem, and what's happening next for us is we're excited to see these efforts expanded as we look at fleet operations across last mile grocery delivery with our partners at Ocado and Asda, as well as pushing forward our own internal fleet development on our Jaguar I-Paces. This is just the beginning, and so please do reach out if you're interested in some of these problems. We really believe it's a space race of our generation, and we've built a really diverse team that's fascinated about these and is a wonderful place to work. So if any of this interests you, I'll put my contact details at the bottom, and I'd be very, very happy to be in touch or chat to some of our team that are around the conference this week. Otherwise than that, thanks so much for listening, and I'm happy to take any questions. Thank you so much again to the organizers for putting together such a wonderful program. Cheers.
Thank you, Alex. Let's take time for a few questions. We're going to start with questions from Zoom this time. Saurabh is asking, to leverage uncertainty, did you attempt to use Monte Carlo dropout in place of using an ensemble? Alex.
Yeah, great question. So we've tried a number of techniques. I mean, there's lots and lots of work that's come out from some of the stuff I worked on 5 years ago, but Monte Carlo dropout is a great way of approximating ensembles. So if you need to be more computationally efficient at training time, that's great. If you've got the compute, ensembles give you, marginally better performance in my experience, but we use both at Wayve.
Thank you.
Hey Alex, thanks for the talk. Quick question regarding the world modeling. You have shown stable prediction in the bird's eye view. How does it look like in the camera view?
That's a great question because it really asks what is the best representation to be able to do to actually imagine the future with. We right now haven't pushed perspective projection prediction forward. We've moved from, well, we had an earlier paper a couple of years ago that was presented, I think, at ECCB, which did perspective projection, world modeling and imagination. We improved the performance by going to bird's eye. I actually think the next step is not to go back to perspective, but go to a latent state. If we can move away from having to go to bird's eye view and move to a more abstract state that actually maybe decodes to raw sensory input, I think that is how you can get better performance. If you think about your bird's eye view, you don't want to represent each, say, meter squared of that bird's eye view with the same representational capacity. I think you can get a more efficient, compact, and powerful representation by learning in an end-to-end fashion what the right things are to represent. And so we're more thinking about how do you push this into a more abstract representation than, say, go back to perspective projection. But if you did want to do that and you did care about that, I think some of the neural rendering work, some of the image generation work is really taking off. And I wouldn't be surprised if you get something photorealistic. And I've seen a few papers come out in the last couple of months that are pushing the boundaries there.
Okay, thanks.
Thank you. All right, take it away.
Hi, Philip Cranfield from UT Austin. Very nice talk. I love it. And I really love how you sort of push simulation to the next level. I was wondering if you can comment a little bit how you would address the gap between the simulated world and the real world.
Yeah, thanks, Philip. That's a great question. So we actually in the past tried to use a machine learning model to align the two. And some of our very earliest work at Wayve was on training something in simulation, deploying it in the real world in a zero-shot setting. And I'd encourage you to read that paper because there was a lot of interesting findings there. But in reality, I think it's there are a couple of things you want to achieve with the simulator. Firstly, you want to be able to show that model A is better than model B in simulation, and therefore those findings will hold into the real world. But then secondly, we actually use our simulator. We train models on real world data and actually evaluate them in simulation. And so you've got to make sure that the representation does align. So there's a number of ways you can do that. You can take a machine learning approach and look to align the embeddings. But I also think there's a bit of an arms race going on where your simulation team needs to be continually pushing the boundaries. And because of the quality in neural rendering today, I think it's less about photorealism, it's more about content realism. How do you make sure that the distribution of objects, if you took a semantic segmentation of both worlds, how do you make sure the histograms match? How do you make sure that there's the same distribution of worlds? And most importantly, that agent behavior is performant. Many ideas like domain randomization looks to make sure that the simulator is a superset of the real world. And if you actually ablate across a larger set of parameters than what you see in the real world, then you can ensure that the real world is captured somewhere within that. But I think it's really about pushing these boundaries and continually applying that feedback as you test between the domains and pushing the boundaries of generalization of your models to new domains like simulation and pushing the realism of your simulator, where I'd advocate for focusing more on content rather than visual fidelity.
Great, thank you.
One more question. Take it away.
Hi, thanks for the great talk. I saw that in some of your videos, the car stops at box junctions. So that's a road rule violation. And so I was wondering, like, what do you plan to guarantee that the self-driving vehicle respect the road rules? By a box junction, you mean an area that's a keep clear for a side traffic?
Correct. The one marked with yellow lines in the intersection.
Yeah, that's a great point. One of the, look, our driver is still learning, but one of the things that's been most exciting to me is seeing emergent behavior over time. I remember, when we just got on the road for the first time and could wobbly drive down and lane follow before learning to go through roundabouts, learning traffic lights for the first time. Each of those steps, you see a behavior emerge that comes from scaling. One of the ones I saw emerge recently was if you come into an intersection and there's no room on the other side for you to go through, our car would actually stop on one side of the intersection and wait for space to clear before it would drive across.
I expect box junctions is something that will emerge soon as well. Although, as you point out, some of the videos, maybe the old ones, I actually haven't checked lately what our performance is in those kind of scenarios. But those are more of some of the more complex scenarios that we expect to emerge over time. Now, the way that we test our algorithms, I think we've built up one of the most exciting platforms where our team can train a neural network overnight, put it through an automatic safety checker testing system that goes through driver licensing, simulation, offline analysis, and deploy it on the car. And you can walk, just over there is our workshop, walk over to the car and go driving around the block. And our offices in central London, you can see all of these amazing scenarios firsthand and see your work physically driving in the real world. That's a process we've got very, very slick at, and I think is a real strength of what we can do. And so for us, testing in a safe and scalable way and seeing these behaviors emerge is what we're focusing on right now. That's a great example of a complex behavior. There's others where you have to do multi-agent navigation and very narrow roads. There's lots of others that we're still yet to learn at scale. And hopefully I'll be able to show some results next year at CVPR that show us nailing those kind of scenarios. But it's a good one to point out, and glad to see you've got an eagle eye on our demo videos.
Thank you.
Thank you so much, everyone.